So let's see, I threw a couple demand curves at you last time. And let's see, we calculated the elasticity of demand, I think. So you guys might need to help me out. I'm just going to put up the one that was on the left panel where, what did we have, 10 and 8? $10 and $8, and what we were doing was moving along a stationary demand curve to calculate the elasticity. The elasticity is what? What is the price elasticity of demand? Give me a definition.
Number that shows responsiveness of quantity demanded to a change.
Good. A number that shows the responsiveness of quantity demanded to a change in price. So we're going to change price by some amount, and that is going to lead to us moving from like point A to point B along the demand curve. At $10, consumers were buying 100. If prices are cheaper, the law of demand told us that, ceteris paribus, they're going to buy more. And so I gave you numbers of 100 and 140. We cranked it through the formula, and we came up with the elasticity equal to negative 1.5. Since you guys have that formula all written out, it's probably worth me doing at least the first step of it, though. Let me put the ratio of the percentage change in quantity over the percentage change in price, and that equaled negative 1.5. That is a number that measures the responsiveness of quantity demanded to a price change. So, what's your question?
I understand that, but like, how can we like apply that to like? You just gave us like a number.
Okay.
Like the quantity or the elasticity of this demand function is 2. What do we know?
Yeah. So good question. So let me. Part of your question might revolve around this. Is this 1.5? What did we have? What was our good? Did we have a good? Did we make up? Give me a good. Any good? Any good? Any good? First thing that comes to mind? What? Hats. So, is this the quantity 1.5 hats? Is this $1.5? Is this 1.5%? What is this number? Might be part of what Raj is asking. Hats per dollar. Your silence is correct this time. Yeah, I see some people holding their hands up. Yes, that's right. It is a unitless number. There are no units. It's strictly just a ratio of two percentages, which actually makes it unitless. So on that definition that I gave you from Wednesday, you might want to sneak in where I put a number, that the definition that Raj just recited, put a unitless number. A unitless number is kind of a thing that's actually helpful because we don't want to get confused by thinking this is $1.5 or 1.5 hats or whatever. It's a unitless number that shows the responsiveness of quantity demanded to a given change in price. All right, so let me just roll with you here and give you the interpretation. The interpretation is actually quite easy once you learn one trick. Another trick in the bag of tricks that I'm revealing to you ahead of time. How can you make any number a fraction? Answer me that question, math people, maybe even non-math people. There is a way to make any number a fraction. How can you make this number 1.5 a fraction? Put it over 1. Good. That's the trick I was looking for. So if we take this number and we put it over 1, the interpretation all of a sudden gets real easy, because check this out. A 1% increase in price leads to a negative 1.5, or I shouldn't say negative, a 1.5% decrease in quantity. It is a negative, but I was trying to get the wording going, and that's what I'll write. A 1% increase in price leads to a 1.5% decrease in sales, or quantity demanded, quantity sold. So the interpretation is this. So let me put down first the key point. Put the elasticity number over 1. Just to kind of make it a fraction. I'll just kind of leave it a little loose lip there, over 1. And so the interpretation is a 1% increase in price leads to a 1.5% decrease in quantity. And it's okay, some questions will think like, you know, quantity sold, if you will, or sales or something along those lines, the volume of product. That's going to be the reaction by consumers. If you drop the price, they're going to buy more, the law of demand. And now we've quantified that by looking at this number and putting it over 1. Sometimes we see people interpret it this way, which isn't wrong. It's just that most of the time economists like to think about small changes. But sometimes if you look at a problem, it's easier to think of a 10% increase in price. If I bump up price 10%, how much is quantity going to change by? 15. See how that's kind of nice? You can kind of go 10 and slide this over 1 spot. That ratio is still 1.5, and now you've got a 10% increase in price leads to a 15% decrease in quantity. Now you've got something you can tell the CEO. When the CEO of Pepsi comes in, you can say, oh, well, this is going to be the effect. Bump this down by 10%, that leads to a 15% change. Right? So it gives a nice, quick interpretation instead of going to the CEO and saying, well, it's a unit, this number that shows the responsiveness of quantity. You know, you need to know that. That's part of your job. But the interpretation to the boss is going to be something that's easy to digest, like this. Okay? Questions or comments there? Yeah?
Does it work the other way?
Yes. So that's why we took it as the average when we calculated it. So a 1% decrease in price leads to a 1.5% increase in quantity. Yes. So you can work those both ways. Yes?
On the elasticity equation, is quantity supposed to be quantity demanded?
Yes.
How come we have quantity, how come it went to quantity sold?
Well, I just put that in parentheses because it might be kind of worded that way, the quantity that people want to buy. Well, if the price was actually dropped by the company, and we have accurate numbers here, then you will sell that many more units because they want to buy them. See what I'm saying? So the quantity demanded is the language that we use from the demand curve. At this price, the quantity demand is 140. So the quantity demanded went up by 40 units. If you actually drop the price, you will sell 40 more units. You know what I mean? So those are just kind of little plays on each other, and you might see a problem that does that. Okay, good question. Anything else? Yeah?
In the homework, there's a lot of problems where it gives you the price, but it doesn't give you quantity demanded. It just gives you if it raises or lowers by a certain percentage.
Okay.
Maybe I'm the only one, but I'm having trouble understanding how
So
to figure that out.
I'm not sure if this would be one, but if you're given this graph and it says suppose the price is $10, then you could use the graph to figure out what the quantity demanded is at each one. And so you might have to fill in some blanks that way. And it's possible, I can't remember if there's any of these, if there is an equation that says the quantity demanded equals this minus 0.6 of the price or something like that. then you could plug in that price and get the answer, which is putting on our equation goggles instead of our graphing goggles. Our graphing goggles say go boom, boom. Our equation goggles say plug and chug, boom, there's the answer. So again, kind of one and the same. Or our schedule goggles that says price and quantity demanded looks like this. I know that the price is $10, boom, the quantity is that. All right, so those are all one and the same, or different approaches to getting the same answer. Does that help? Is that the kind of hole that they had that you're thinking of, or was there another one?
I'm not even sure.
Okay, so, but just bear that in mind that there can be little pieces of the puzzle as we go, and we're going to do a few more examples here today, that you need to fill in the gaps here on whether you're using the percentage change. If they said that, as long as you brought it up here, let me do a quick little different example. Suppose the elasticity of demand equals negative 1.5. And price increases 7%. What is the impact on quantity demanded? So this would be maybe a way a question could be worded. Suppose the elasticity of demand is negative 1.5 and price increases 7%. What is the impact on quantity demanded? How do we go about solving this? Okay. I'd stop you there. You could start doing it that way, but there's a simpler way. Do we know this? Yes. Do we know this? Look at the question. No. Do we know this? Yes, we got that. So we're going to solve for that. All right, so we're just doing a simple little algebra problem of, from this problem here, I'm going to write it down here just to, negative 1.5 is the elasticity. I've got the percentage change in quantity that I don't know that I'd like to solve for. And I've got the percentage increase in price is 7. Put a 7 down here. And if I now bring the 7 over here, 7 times 1.5, I can calculate that the percentage change in quantity demanded is equal to negative 9.5%. And I know that that's a percent. I can kind of double check my work to say, oh yeah, it does. If I plug this back into here, is 9.5 over 7 equal to 1.5? And I can kind of double check my work to make sure I did it right. So that would be a 9.5% decrease. You will see problems like that. So questions there? You guys, you can sneak up to the extra chair. It looks like one's ahead of you if you want. I don't mind you standing up. I just thought I'd mention, feel free to move around if you need to get a little closer. Okay, any questions? All right. So, what if we do it again? You guys, like I said, you're going to get a little more practice here. If I do another price change from 8 to 6, what is this number? Putting your graphing goggles on, assuming this is a straight line. 180, good, right? So the slope of a line is constant. Rise over run is going to be constant. If I was down 2 over 40 here, and I go down 2 again, I'm going to go over 40 again. So this number is 180. Now, what would be the elasticity between B and C? What do you think the elasticity would be? Same. I think I heard somebody say, right? So let's calculate it. I know this might be boring, but I really want you to apply the elasticity formula. This is a good double check that you actually know what you're doing instead of knowing what you're doing. So take the time. I'm going to come around and see how you're doing. Go back to the big ugly formula that you should have on your notes that I will rewrite again here. It's the new quantity minus the old quantity divided by the average quantity, and the new price divided by the old price divided by the average price. So plug and chug. Prove to yourself that it stays the same at 1.5. Anyone help getting started?
Oh, no, I got it.
Okay. Okay.
Low price is 8. So it would be.
So one thing you might want to do is put the new quantity is 180. So it's 180 minus 140 divided by the average of those two, which you can kind of do in your head maybe in between. What's the middle number in between it?
Oh, in between here?
Yeah, 160. So that what we did is we picked off the middle number. That's the average. So the average quantity is so divided by 160. Now all of that divided by the new price minus the old price. The new price being 6.
The old price first
Yep.
thing.
So then kind of start working it there. Yeah, I just went down again. So I put the new quantity is 180. So your first number should be 180 minus
So
the
would that be-
old quantity, which is now 140.
So the average is that'd be 7.
Average of those would be 7, yep. Okay.
And then I get stuck because I'm bad at math.
Okay. So that looks good. Okay. So then the next math trick, if you keep it doing fractions, and I mean you can pull out your calculator with this. So you might want to do that, but you flip the denominator, multiply it times the numerator. Flip that sucker over, and now you're multiplying this one times this one, and then solve that. But feel free to pull out your calculators if you.
It's not as hard as I thought it would.
Okay, good, good. Yeah, I know. Sometimes you guys, that's why I really want you to kind of approach it yourself. A lot of times it's a lot easier than you think it's going to be. It's like once you jump into it, the formula can be intimidating, but it's not too bad. So what are we, did everybody get in 1.5? No. What are you getting? 1.14. What else? Who else? What other numbers are you getting?
Negative 7/8.
Negative 7/8. And what's 7 divided by 8? Somebody with a calculator.
Negative. Yeah, I got negative 7/8 too.
Negative 0.875. Okay, how many people got 7/8 or the fraction of that? I'm seeing a lot of hands go up. Okay, good. So, come on, cameraman, stay with me. So, the elasticity of demand equals the difference of the quantities, which was 40, divided by the average of 160. The difference of the prices, which was -2, divided by the average, which was 7. So this equals 4/16 times 7/2. Cancel that, equals 2. We get 14/16, which equals 7/8, which equals negative, and yeah, I had a little negative sign that I probably should be capturing along there. Negative what? 0.875. That looks right. Thought it was the same, but it's not. So that's what I wanted you guys to kind of figure out on your own, is that that number changes at different spots along a demand curve with the same slope. The slope of the demand curve, as we said, does not change, but the elasticity does. That's an important concept. So the elasticity of demand varies along this thing. So you might want to put here at this middle point here, the elasticity of demand was equal to the -1.5. And here, the elasticity of demand at this point was equal to -0.875. So over this range, if we were to interpret that number, A 1% increase in price leads to a negative or a 0.875% decrease. So just following this exact same logic, we just say a 1% increase in price leads to a 1.5% decrease. Now it would be a 0.875% decrease. Okay, good. So let's see the direction that it heads and why it does that. Let's go down here. Imagine we were down here at $1 and $2. I'm going to get away from the $2 thing, but just say $1 and $2. If you were at $1, if the price was $1 and it went up by $1, roughly what would be the percentage change? Kind of going back to old school methods. It was $1, now it's $2. What's the percentage change? 100%, yeah, it doubled, right? So it doubled by the amount it was. So the percentage change over here would be kind of like 100% or something really big, approximately 100%. And likewise, if I'm down here, I might be moving from a big number like 260 with the change. So the percentage change down here is something small. Because we're dealing in percentage changes, that's the way this thing works. As I move up here, even at $10, and I add $1, now that $1 is just a 10% change, roughly, again, going back to old school methods, right? So as I move along the demand curve, the percentage changes move around. And that's what gives us the elasticity covering different ranges. All right. Well, let's try to clarify that and the importance of it through looking at one of my favorite graphs in economics, the connection to total revenues and the demand curve. The reason I like this one is because it brings in a business element to it in a very direct way. How do companies calculate profits? So my first question is just kind of a question. What do profits equal to? If you're calculating how much money you made in profit, what do you do? How much money you spent, so total cost, versus what? How much money you've taken in, right? So the total revenue, the amount of money in the cash register at the end of the day. So profits are equal to total revenue minus total cost. How do we calculate the amount of money in the cash register? Yeah. Profits. This will be my shorthand notation for profit. In macro class, I know a few of you had me for macro. What is it in macro? Inflation. Yeah, so sorry to screw around with you, but my professor did it to me, so this is my payback somehow or something. So profit is equal to the difference between total revenue and total cost. How do you calculate total revenue? What's that? Total revenue, amount of money in the cash register at the end of the day. How do you calculate it? So let me put you back to a point in time where you had a lemonade stand. How many of you had a lemonade stand when you were little of some sort? Maybe it was Kool-Aid or whatever you were selling, right? So if you sold 40 glasses of lemonade at $1 a piece. Now you were probably doing a quarter, but I'm trying to keep the numbers easy. My son actually charged $1 and made at least $100 to $200 every football game up at Iowa State, because there was 10,000 people that were passing by our door, and here's a cute little kid selling lemonade for $1 a glass. So he made a ton of money when he was 5 years old, up till the point where we left Ames. So he had a nice bankroll, bought some nice stuff. So how did he calculate his revenue? How much money was in the little jar? 40 glasses, $1 a piece. How much did he have? $40, right? So what he did is he took price times quantity. Price times quantity gives us total sales revenue. Total revenue. All right, we'll talk more about total revenue later, and then whatever our costs were, we'll shelve that for now too, because what I want to get into is this graph here. I want you to stack two graphs on top of each other. The upper graph is the demand curve we just got done doing. So the upper graph has price and quantity, and then just go ahead and draw yourself some demand curve. For this one, go ahead and draw it so that the demand curve touches both the vertical and horizontal axis. For the most part, I don't care where that is, but maybe make it somewhere off to the right here. So where it intersects the horizontal axis is some quantity of product. I don't know what it is. Let's just call it Q1. That quantity corresponds directly to the graph downstairs with this quantity, Q1. Let's say it's 100 units. So there's 100 glasses of lemonade. So we're also measuring quantity in the downstairs graph. On the vertical axis of the downstairs graph, we're going to measure total revenue. So total revenue is price times quantity. Now, first of all, step back from this and think about what's going on. I've got price and quantity here showing the demand relationship, and I've got price times quantity, the interaction of those two variables, on the vertical axis here. And of course, this quantity is just the same. So we're going to look at how revenues change as prices change. And it's going to all tie in together with the elasticity of demand. So, as an anchoring point, just bear with me. I want you to take, however you drew your graph, find the midpoint between the intersection of the horizontal axis and the origin. Find that midpoint. And then go up to the demand curve. Go straight north until you bump into your demand curve. That represents a special point. There's one point along here where the elasticity of demand is equal to 1. And that ends up being the spot where that happens. So the elasticity of demand is equal to -1. The next thing I'd like you to do is drop south and then stop, like maybe here, and just put a point. Just kind of make it somewhere kind of high on the upper portion of your graph. And then I want you to make the revenue mountain, the mountain of cash. And that mountain of cash looks like this. It goes through that point and comes down and ends up there. There's your big old pile of cash. Now, what's happening to that pile as we start to sell more product by lowering our price? What happens to the actual pile? It gets higher as we're moving this way. I'm making more money, I cut my price. I'm making more money, I cut my price. I'm making more money, I'm dropping my price. Eventually, what happens to my pile of money, the amount of money in the cash register, remember this is cash register money, it starts to go down. And you can kind of figure that out here. Once I start charging 3 cents for my lemonade, I have lots of buyers. But am I making any money on it? No. Not in terms of the revenue that's coming in. If I take the 3 cent price times 1,000 glasses, 1,000 times 3 cents is 30 bucks. Okay, so not a lot of money. So this is correlated with points along the demand curve that are very important for decision making and related to the elasticity. If I pick a point up here, point A, and I decrease price by $2 from, I guess I'll go 12 down. I kind of want to take it away from the examples there. If I go from $12 down to $10, point A and B are connected to points A prime and B prime down on the revenue graph. So points A prime and B prime are connected on the revenue graph. I just want to get these so that we can see that good. And so a decrease in price when the elasticity of demand is greater than 1, like it was over here, that leads to an increase in money in the cash register. However, if I take another price decrease, maybe down here, from $2 to $4, if I drop my price at points C and D by the same $2, the money in the cash register falls from point C prime to D prime. So in short, a lot of businesses make this mistake. They want to make more money, and so they cut price. But that's a dumb thing to do. If demand is like this, they should actually be raising their price. And we will move this way up the money mountain here of revenues, right? It'll just move the opposite direction. So that's why these elasticities are important. Let me pause there for a sec. Questions on how this thing functions. If you memorize this graph, you can answer lots of different questions that come up on multiple choice. So if you can actually point blank I recommend that you memorize this graph. And that'll bring you a long ways in terms of knowing how to answer a question when it comes up with elasticities in their relationship to revenues. I've got a couple more things to add and then to come back to as well. So over this range of demand, as we start to get this way, what does the elasticity number approach but never get to? 0. Good. So if we look at the elasticity of demand number, when price was down here, this number was really, really, really big, right? Like 100%. So this number's getting big, this number's getting small, which is making the whole thing get kind of close to 0 as we move this direction. So when the elasticity ranges from 0 to 1, we say that demand is relatively inelastic. This is the inelastic range of demand. The inelastic range of demand. In order to get an elasticity number that's greater than 1, I got it. There's one other thing I need to clean up. Greater than 1 in absolute value, but we'll talk about that in a sec. That was my other cleanup thing. If we get a number up here where it's bigger than 1, ignoring the negative sign, then that is the elastic range. The elastic range of the demand curve. Again, using our math that we're hopefully starting to become a little bit more comfortable with, if I look at this formula, in order for this expression to be greater than 1, the upstairs has to be bigger than the downstairs, right? So the quantity changes are going to be big for relative to the price change in terms of percentages. All right, so let's summarize that here. So if the elasticity of, oh, wait a second. Let me, before I do that, I want to clarify this negative sign business. This is another thing that's not my fault. It's just the way somebody did it long ago, kind of like our demand curve with Alfred Marshall. Because we all know the law of demand, which is what again? As price goes up, quantity goes down. As price goes down, quantity goes up, ceteris paribus, but the law of demand. Because we all know that that's a negative sign there. And so we ignore it. And we treat it as a positive by taking the absolute value of it. So in the elastic range, the absolute value of the elasticity is greater than 1. Absolute value, remember that just strips out the negative sign. Not too big of a deal, but that's how we express it in written form, which is what I expect you to do unless it's otherwise stated. So the absolute value is greater than 1. This is not wrong. The elasticity of demand is really -1. The way I have it written, that's absolutely correct. So will be your homework and test problems. If you write it this way, that's okay. But when we verbalize it, we tend to strip that out because we all know it's negative. Okay, I know that's a confusing point. It's been a tough one for me to continue to do every year, but you will get there. We're just adding little baby steps here to get you there. So in the inelastic range, the elasticity of demand in absolute value is less than 1. It saves us a lot of grief actually with thinking about the number line, and because technically a bigger negative number is actually smaller, so it just gets kind of ugly if we start talking that way. It's actually easier to talk in absolute value. All right, so let me come back to writing this now in terms of absolute value. If the elasticity of demand is greater than 1, then the percentage change in quantity demanded is greater than the percentage change in price. The upstairs is bigger than the downstairs. And demand is relatively elastic. Demand is relatively elastic. If the elasticity of demand in absolute value again is equal to 1, then what's true about the percentages? They equal each other, right? So if this is 7%, this is 7%. If this is 6%, this is 6%. If this is 1%, this is 1%. It equals 1. So the upstairs equals the downstairs. And notice what happens with revenues is that at that point, that particular price change in a very small increment has no effect on total revenue. It's kind of the tipping point, right? So that's kind of a critical tipping point. When the elasticity of demand equals 1, then these two things equal to each other, and demand is unitary elastic. So unitary is kind of just this pivot point. 1 unit is the idea of the term there. Unitary elastic, it's equal to 1. If the elasticity of demand is less than 1, then the upstairs is less than the downstairs, and demand is relatively inelastic. Questions? Comments?
Can we do the next problem?
We will do one up in a little bit. I'm going to tackle a little bit softer topic that I hope will start to gel some of this together next before we do another numbers problem. I feel like we've had a lot of numbers so far. I see some faces that are looking a little exhausted, a little glary-eyed, a little something here. So let's move into something fun like extreme econ. We got all those extreme sports. You know, we've got the snowboarding, which is almost mainstream now, and snowmobile jumping. And so now we're going to watch how economists get crazy with some extreme elasticities. So what if the demand curve looks like this or this? I know this is getting wild. I should probably have a rating on this, like this is like R-rated or something.
The price has no effect on the quantity.
Okay, so yeah, we're going to look at where they're independent of each other, right? So these are some situations where the price and quantities don't quite behave the way we were thinking with changes. So what is the elasticity of demand when it's perfectly vertical like this? Look at your formula. The elasticity of demand is equal to the percentage change in quantity demanded over the percentage change in price. It's good to rewrite that thing a lot of times during this to just have that memorized. Well, let's pick off a couple points like we did. Let's just call it P1 and P2. So I got a couple numbers. Maybe it's 10 and 12. Maybe it's whatever. It doesn't matter. And then the thing that catches our attention here is that Q1 equals Q2. If this was 100, quantity doesn't change. So are consumers responsive or unresponsive to price change? Unresponsive, right? There's no response. So this is one of these extreme cases again. All right, well, let's work through the math. The price would be some number, and the quantity is 0. So 0 divided by some number equals 0. So under this extreme case, the elasticity of demand is 0. All right, let's do the same thing over here. So we got point A to point B. Now we've got P1 equals P2. And quantity jumps up from Q1 to Q2. We go through our formula. Percentage change in quantity. Is it 1? We got, let's see, some number divided by 0 equals 0 again, right? Oh, you can't divide by 0. That's right. That 5th grade math teacher comes ringing in your head. Remember this, you can't divide by 0. It's just a rule that you got to follow. She didn't give you a reason why. She just said that's the rules. That's the rules of math. You can't divide by 0. So now that you guys are in college, though, we're going to be a little more clever. And let's divide by something that's really close to 0 to trick that old math teacher from 5th grade. So what I'd like you to do is divide this by 1 over 1 million, like 1/1,000,000th. That's pretty good. So, all right, so we can't divide by 0. I'll agree with that. But what if we divide by 1 over 1 million? I see some of you are still kind of uncomfortable with that. And so if you're uncomfortable that that's not far enough away from 0, get a little closer to 0. Divide it by like 1 over 1 billion. Or those of you who are really creative, if you want to go over 1 trillion, in other words, you get as close to 0 as you wish, right? Make this number as close to 0. If we're looking at a number line, there's 0, there's negative infinity, there's positive infinity. You just keep snugging yourself up to 0. But don't undergo there, because the 5th grade teacher said it can't be 0, but get it really close to 0. And as you get closer and closer to 0, what happens to this expression? Some number divided by something very, 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 very small. How do we solve when we have a fraction in the denominator? How do you solve a fraction in the denominator? Let me pick on Sarah because I just told her this when I was walking around before. What did we do to that fraction in the denominator? We flipped it and multiplied it times the numerator. As you flip this, then all of a sudden it's some number times a million. But if you were uncomfortable with that, then it's some number times a billion. If you're still uncomfortable, it's some number times a trillion. In other words, it's as big as you want it to be. It's infinity. Okay, so we can say that this expression is essentially equal to infinity. It just blows up on us because we can make the denominator as small as we want it to be. And there's your extreme cases. So we said that this one's unresponsive, and so this demand curve is what we title perfectly inelastic. Perfectly inelastic. And good, I have it. And this one is perfectly elastic. Now, reality usually brings us somewhere in the middle. So there's our extreme cases to kind of give us a reference. But in reality, we might have a couple curves that look like this. One that looks like this, and another one that looks like this. Right? Pretty vertical, if we think about it in that way. Pretty steep, but not perfectly steep. Pretty flat, but not totally flat. What did we learn about the range of elasticities along a downward sloping linear demand curve? How do they change? All right, so nothing different's going on except for this one's a little bit flatter. And now we think that this is a relatively elastic demand. Relatively elastic. This one's relatively inelastic. We call it that because we can still break it apart. If I take the little midpoint thing, just like I did here, up here, right there, is unitary elastic. And this portion up here, I used to write on the wall back in the days, but I got myself in trouble. So up here is the elastic range. So my point is that we have the same thing going on, but when they get pretty steep, all the relevant detail is in the inelastic range. Same thing's going on here, is that this demand curve actually continues down here. And if I take the midpoint, it's right here. And so there is where the elasticity of demand is equal to 1. But over all the relevant ranges of the demand, all of those numbers are going to be bigger than 1. And so we say that this demand curve is relatively elastic. Okay? Questions there? All right. let's see. I think it's time to bring in, you guys have been having so much fun with these elasticities that we need to bring in some new ones here. Let's, and then we'll work some problems to make sure we got this stuff down. All right. What are the demand shifters? This is back from earlier this week. Actually, it was last week. I think we did it on Friday. But demand shifters that we all have memorized for taste of preferences, related goods, price of related goods. Be careful. Price of related goods. What's that? Population. Good. That's 3. Income. Good. That's 4. Expectations. Yes. Those 5 things were our shifters. And now we can use elasticities to measure those responses more quantitatively too. So the first one we're going to look at is the income elasticity. The income elasticity. The formula, another formula for you to memorize. You're going to see some similarities. So really, you memorize one, and I think you've got it down. It's the percentage change in quantity that occurs, and this is quantity demanded because of the income, that occurs from a percentage change in your income. So if my income, if I get a 5% pay raise, how much more Budweiser do I buy? Right? That number is going to capture my responsiveness to income changes and the purchases I make. All right, so let's just do a little example here with this one. There we go. So let me give you the definition first. It's a number that shows the responsiveness of quantity demanded to a given change in income. So if you look back at the definition of the price elasticity, all we've done is substituted in that single word. And that's why the formula looks awfully familiar as well. So let's do this one with an example. Suppose that there is an elasticity of demand. I'm sorry, a income elasticity. Suppose the income elasticity is 1.2, and per capita, which is per person, per capita income rises 10%. What is the impact on steak? And I forgot to tell you, this was the elasticity, income elasticity of steak. So, what do you got? 12%, right? So, we're going to use that same trick we did before. I kind of chose the numbers to be fairly easy here in terms of the 10. We got income rising by 10%. We got a 10% down here. This equals 1.2. So what does this number need to be? 12. 12 divided by 10 equals 1.2. So we can maybe look at this one, but if we're going to solve it a little more formally, we'd put the math together with it. So we've got the income elasticity of 1.2 equals the percentage change in quantity divided by the 10%. And if you want, you don't have to put the percent down, just to kind of just look purely at the numbers, since that's the percentage change in price. So that leads you to solving this. 10 times 1.2 equals 12. We get a 12% change. Now, I left off the absolute value thing here. So is this actually supposed to be negative? I kind of forgot that step. What about the negative business with this one?
You would change 10 to a negative 2.
10 to a negative 2.
No, like the negative also.
Like this should be negative?
And then you would do negative 10 times negative 1.2. Now you get positive 12.
Okay, so then that would change it then? Is this right or wrong?
You probably don't even have to show the negative because it's just showing the change.
It's
Okay.
just a percentage change, so
Okay.
it's 12%.
So is it possible, is this thing always negative or is it supposed to be positive? With the demand curve, remember I gave you the whole song and dance of it's always negative, so we always know it's positive, we talk about it positive. Just want to clear up what this is going on here. What's that?
It doesn't matter because it's just a change.
It does matter. It turns out to matter. So you guys, if you're thinking about the percentage changes, that's not really the issue.
Isn't it, I can put it up here, isn't it positive because the income is rising, so that means the sales are safer, right?
Okay, good. You're hitting right on it. So income's going up. I love that you're digging down to your gut and you're kind of looking at the interpretation of what does it mean to be negative or positive. Instead of getting hung up with the formula, if incomes are going up, am I buying more steak or less steak? More steak. Does that mean income elasticities are always positive? No, we learned that from the shifter example from chapter 3. As my income goes up, I might choose to buy less of stuff. Like what? Inferior goods. Ramen noodles, hot dogs, other things might be going down because I'm buying less hot dogs and I'm buying some more ribeyes, right? So the ribeye purchases are going up, but the hot dog and ramens is going down. And so with the income elasticities, sign matters. Not size. Sign. I don't want to have that discussion here. So sign matters, right? So if the income elasticity is positive, what is steak according to economists?
A normal good.
A normal good. Good. As income goes up, purchases of the good go up. It's a normal good. So if the income elasticity is greater than 1, positive number, greater than 0. Switch that on you. Remember, it was 1 was our anchoring point before with demand. If the income elasticity is a positive number, then the good is normal. It's a normal good. If the income elasticity is a negative number, like we might expect for hot dogs and ramen. Income goes up, I buy less of them. If the income elasticity is less than 0, then the good is inferior. And it brings up our two cases that we had in our shifter list of normal and inferior goods having a different impact. And what if the income elasticity was equal to 0? What if the income elasticity was equal to 0? What would that tell you about the relationship between
There is no.
income?
We're not buying it either.
Yeah, how sensitive is it to income changes?
No.
None. So in other words, when you guys get your first job, maybe some of you will be lucky enough to get a $40,000 a year job. Think you're going to buy more milk? Even being a poor college student making a 6-pack of Red Bull every day, are you going to have your bowl of milk and then all of a sudden, I got to have more milk now that I'm rich? No, milk tends to be pretty stable and independent of our income. So if the income elasticity is equal to 0, then the good is not sensitive. The good is not sensitive to income changes. So, example, milk. People tend to consume the same amount of milk whether they're rich or whether they're poor. And so those income elasticities will tend to be close to 0. All right. Since we're having so much fun, let's do a cross-price elasticity. Cross-price elasticity. The cross-price elasticity is a unitless number, a number that is unitless. I'm just going to put up here a number that shows the responsiveness of quantity demanded to a given change in a related good, the price of a related good. All right. That number is calculated, hold on tight, another formula to remember. Looks awfully familiar, right? What's the percentage change in the quantity versus the price of a related good? If you want to, with this definition, just to keep things similar, we might have the quantity of Coke versus the price of Pepsi, right? For example. All right. So let's do an example with this one. Suppose that the price of beer falls by 10%, and the sales of wine increase 12%. Suppose that the price of beer falls by 10%, and the sales of wine increase 12%. Calculate the cross-price elasticity of wine. As soon as you got an answer, shout it out. Let's hear it. Negative 1.2. 1.2. Oh boy, here we go again with these doggone signs. So, what do we do with the signs here? Let's first of all look at the numbers, and you got to read carefully what's going on here. So the cross price elasticity is the fraction of quantity over the fraction of a price. Which goes where? If we're looking at the cross price elasticity of wine, what goes upstairs, what goes downstairs? What good are we measuring with each? Wine goes up, okay? And the price of beer is down here. So we're thinking about how responsive wine sales are to the change in the price of a related good. And that related good here is beer. So now we got to be careful again by reading the question. Where does the sign, if it plays a role at all, where does it belong? So what do we do upstairs? Positive what? 12. So I think we all were starting to see that. So we got positive 12. And downstairs we've got, are you sure? Are we 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 sure? Come on, we've got a football game tomorrow. Let's get a little chant going. I want to hear yes. If you're sure, say yes. Are you sure? Are you sure? All right, good. It's a negative 10. And so what do we get in total? What does this equal? Negative 1.2. Are beer and wine substitutes or complements? According to this data, are beer and wine substitutes or complements?
Substitutes. So it's the related good.
Let's try our interpretation here. Interpret this number for me. Look at your interpretation. You can use this. This isn't the right thing, but follow this logic. Go ahead and write it down. Wait, sorry, not that one. The one that I've already erased. A 1%, start off there. That's how it starts off. A 1%, ... You guys fill in the dots here. This is the interpretation of this number of 1.2 that you gave me. So interpret the 1.2. Write it down. Follow your gut. Follow your logic. Remember the little trick. You can put this over 1. Put this over 1. Are the two substitutes or complements according to the data? This data here, that our cross-price elasticity ended up being a negative 1.2.
Substitutes.
Why substitutes?
Because as beer decreases, wine tends to increase.
So as the price of beer decreases, the quantity of wine increases? So that makes them substitutes. Beer is cheaper, so I buy more wine? That's what you just said. beer is cheaper, so you buy more wine. Is that complements or substitutes? Look at your definition here. A 1% increase in what? The price of beer. A 1% increase in the price of beer leads to a 1.2% decrease, because of the negative sign, in the quantity of wine. There's your interpretation. Beer gets more expensive and I buy more or less wine? Less is what the negative sign means. Beer and wine are complements or substitutes? So I like to have something right off the top of my head. If Pepsi gets more expensive, do I buy more Coke or less Coke? More Coke. If peanut butter gets more expensive, do I buy more jelly or less? Less. So which one has a negative sign? Complements or substitutes? Complements. Peanut butter and jelly go together, and they have a negative sign. The data here is saying that beer and wine are complements. Now, the reason I like to bring this up, for you guys, maybe it's substitutes, but sometimes we approach problems in economics when we do sophisticated research or maybe just little research, and we come up with counterintuitive answers, and that's why it's called research, right? So our gut feeling is one thing, but that's called cheap talk. What economists do is look at the data and do some analysis and come up with an answer that's supported by data. Now, I just made this number up, but I'm saying that's kind of a way that things go about here. And now you might start to think, well, you know, if you think about it, if you're having a big party tonight, you're expecting 100 people. What do you want at your party if you are choosing to provide alcohol? What might you want to have? You've got lots of gals and guys coming, and you got 100 of them. For your party, what might you want to buy? Tequila, yes. What else? Beer, vodka, whiskey. What else? What else might you want to have? What might the women like to drink especially? Some wine. Right? So maybe we do tend to buy these things together. We can start to tell a story that, well, maybe that's not so far-fetched. That if beer is cheaper, we might go to the liquor store and actually buy more of both. Right? We might buy more beer and more wine. All right, so that's our cross price. So once again, sign matters. Sign matters with the cross price elasticity. So, if the cross price elasticity is greater than 0, then the goods are substitutes or complements. If the cross price elasticity is greater than 0, it's a positive sign. Substitutes. The price of one goes up, beer goes up, and I'm buying more of the other good, right? So one gets more expensive, I start buying the other one. That gives it a positive sign, and so they are substitutes. And we need to, next time if you guys come through the back door, I'll try to remember, I've been doing it just to keep that back door wedged so you guys can come and go if you need to take a little breather. If the econ's getting too hot, you got to get out of the kitchen. That's what I start saying, all right? So if the cross price elasticity is less than 0, then the two goods are complements. If the cross price elasticity is equal to 0, what's true about the relationship of the two goods? They're unrelated, right? So then they are unrelated. And that gives us our cases. All right. So these are the ones that your book goes through. You can also have elasticities for really anything that's important. We could look at the elasticity of age. Was it this class that somebody brought up, like as you age, you might change your preference? Jenna, did you say that?
Yeah.
Yeah, that's what I thought. So we could have an elasticity of purchases with respect to age. Might be an interesting thing to look at. We want to know how responsive our sales will be as people age. Are they going to start to fall off? Do I need to market more to young people so that as they age, they start to think about the product? Where do I place my advertising? Do I put it where old folks go? You know, do I put a big billboard right above the old folks' home? Or do I put the billboard over by the high school? Right? So where I place advertising might be relevant to things like age. And so my last comment here on this section would be, you can do an elasticity for just about anything. For just about anything. So for example, age. Well, the age elasticity would look something like this. Percentage change in quantity divided by the percentage change in age. We just take that variable and we see how sensitive people are to changes of their purchases with respect to age. And we can collect data on that and see what happens. Okay. So we're going to go back to, no, we're not yet. Actually, we've got one last little comment here. We have spent all of our time on the demand curve. We've left the poor suppliers alone. The elasticity of supply. Is a number that shows the responsiveness of suppliers, quantity supplied, to a change in price. So the formula would be the percentage change. Now here's where it's different upstairs. We're going to be talking about the supply curve, so this is the percentage change in the quantity supplied over the percentage change in price. All the rest of it follows, the averages, all of that stuff. I'm going to leave that off. So it is a number that shows the responsiveness of quantity supplied to a given change in price. So with the supply curve, we're going to have very similar features to what we did with demand. Let's put three graphs side by side. Over here, I just want you to put a relatively steep supply curve. Kind of maybe some sort of regular supply curve over here. And then this one you can make kind of flat. Which one's more elastic? The one to the right, the one to the left? The one to the right. That's right. So we're getting a bigger response. See, you guys are learning already. We got the same sort of properties going, the flatness here. So with this one, for a given change in price from $10 to $12, suppliers are like, I'm all over that. I'm going to respond with a big change in quantity supply. Right? So this one is relatively elastic. And this one is, again, relatively inelastic. Now, I'm going to give you one of my greatest inside secrets to remembering this. If we look at this curve, as it starts to get steeper and steeper and steeper and steeper, it starts to look like a I for inelastic. Awesome, huh? As it starts to get steeper and steeper. Now the same thing holds for that demand curve. So as I got a demand curve, if I was to add one here like the golf club, as it starts to get steeper and steeper, it too starts to look like a I, relatively inelastic. All right, so remember that. That'll kind of help you when you see some stuff. What's that? Why didn't you say that earlier? That would have helped? Okay, well, I didn't think of it at the time. I would have let you have it if I could. So, all right. So, the flatter they get, the less of an I it looks like, so it's more elastic, more flat. All right, so one thing that is a kind of a key thing to remember from the elasticity of the supply is the amount of time it takes for somebody to adjust their supply. So one of the key points that, let me just write that out here. Kind of a key point is that the amount of time we allow for adjustment affects the elasticity of supply and demand. So it works for both sides, but I wanted to start with the supply curve. So if we think about the amount of product that's on the shelves at Walmart of something that all of a sudden becomes a hot item, like umbrellas or something, and people are flowing through the door, the quantity of umbrellas at Walmart right now today is probably perfectly inelastic. In other words, Walmart can't pick up the phone and get new umbrellas in today, or within the next hour, or within the next 4 hours. You see what I mean? So as I shrink the amount of time, the umbrella supply curve looks more like an I. Now if I say, what's the supply of umbrellas over a week? Well, Walmart can just about get umbrellas from somewhere around the world in a week, right? They can call up the supplier and get them in. And so the supply curve might look much more flatter for a week or a month or a period of time. So as more time elapses, the curves get more elastic. So more time leads to a more elastic curve, whether it's demand or supply. Getting back to our party example, since it's Friday night here shortly, if you've got that party going on and 100 people are coming in 3 hours, and you go to the liquor store and you find that, whoa, they really jacked up the price of Jack. There goes my whiskey, but everybody's depending on me to have Jack Daniels at this party. Do you have time to go shop around other stores? No, maybe not. Your demand for Jack Daniels that day might be fairly inelastic. Whatever the price of Jack is, I'm going to pay it. If it's 45 bucks, if it's 30 bucks, if it's 50 bucks, I got to have it. My demand is pretty inelastic. I'm unresponsive to price changes. Now, if you give me a week, if I'm a planner and I didn't do this last second, and I'm thinking about the party I'm going to have a week from now, and I go to the liquor store and I'm like, whoa, are you crazy? That's way too high. I go the next day to some other place. You see how I've allowed myself more time to find alternative substitutes for the good. So that's how time affects the elasticity. And here's a couple other. So let's see, this is, I guess, kind of number one. Number two would be the availability of substitutes. The availability of substitutes. So, if I go to the store and Jack Daniels is high, what might I choose to do as a consumer? Find another dark liquor. That's right. So there might be a Canadian, I might go up to Canada for some Canadian Club, or I might buy some Kansas whiskey, or I look down the shelf at the bottom of the barrel here, some Knob Creek, whatever. If there's if the store's got a pretty good selection of whiskeys, I'm just going to switch around. Now, how does that influence my demand for Jack Daniels? Does it make it flatter or steeper? Flatter. So let's check it out here. If I think about the availability of substitutes and I put a demand curve that's kind of flat and a demand curve that's kind of steep, if I have a whole bunch of substitutes available, then when good old Mr. Jack raises his price from $20 a bottle to $30, I say, see ya, and I go buy some other brown liquor, right? That means the demand curve is relatively flat, partially due to the availability of substitutes. The more options I have as a consumer makes the demand curve flatter. All right, so availability of substitutes. More subs means more elastic. More substitutes means more elastic. It's going to be flatter. Now, another thing that's related to this one is how we define the good. If I look at the demand for whiskey versus the demand for Jack, which demand curve is more elastic? So using these two generic ones I have here, it's kind of like saying which one's the Jack demand curve and which one's the whiskey demand curve. The one, let's call this A and this one B. Which one's the Jack demand curve and which one's the whiskey demand curve? Go ahead, what's that?
Jack would be B because like it's just that one brand.
Because it's just that one brand?
And then A would be whiskey as a whole.
Okay.
Yeah.
Does everybody agree with that? I'm looking for somebody to disagree with that. Good, Jeff? Why? What do you think?
Well, given your example with A and B, if he raises the price, the line's flatter. But if you're talking about whiskey as a whole, I'm going to buy another brand of whiskeys, the line's going to be steeper.
That's right. So, Jack is a type of whiskey, right? Jack is a type of whiskey. If I'm a brown whiskey guy, and Jack is more expensive, and I flip over to Canadian Club, right? I'm still buying whiskey. In other words, for the good defined as whiskey, there is less substitutes. Because I might, by the way, go to vodka or go to beer or wine or something else if I feel it's a substitute. I have all those substitutes at my disposal when it's Jack too. So when I look at the bottle of Jack, I have my substitutes are all the other kinds of whiskey and all the other kinds of vodka, beer, and wine that I can buy. If I look at whiskey, my substitutes are just the vodka and the beer and the wine. So in terms of following this logic, there's more substitutes available to Jack as opposed to whiskey defined that way, more broadly. All right, so related to this here is, let me write this up here so I got it in a good spot. So note, the more narrowly a good is defined, so from our example, Jack is more narrowly defined than whiskey in general, right? The more narrowly defined, the more narrowly a good is defined, the more substitutes there will be, and therefore the more elastic the demand will be. And I don't think I'm doing real good English here, but I kind of run on with that one.
The scarcity of good is scarcity of good.
Yeah, the more we drill down to an exact type of good, there's lots of substitutes available. So from our example, Jack has subs of other whiskey, vodka, and beer. I'll just abbreviate here a little bit, and it may be some other things. Whiskey has subs of just vodka, beer, and other things. All right, questions on that one? So you'll start to see this in some of your problems, and maybe those of you who read ahead, you saw this in part of those descriptions there in your book. All right, last thing, number 3, is the fraction of income spent on the good. The fraction of income spent on the good plays a role in the elasticity. When gum prices skyrocket 20%, do you change your purchases very much at the cash register? When gum prices go up from $1 to $1.20, are you like, no way am I buying gum again? Or do you not even really think about the price or look at the price and you just say, hey, here, I'll have some of this, right? The fraction of your income that goes towards gum spending is very small. So you tend to be insensitive to price changes. Demand is fairly inelastic for things that make up a small fraction of your income.
That's why people always notice like trash prices going up a couple things.
Yeah.
But you never notice like maybe the quick trip went up to like.
Yeah, the quick trip you just kind of maybe ignore. So the larger the fraction, i.e. a brand new car, if your $10,000 car goes up 20% from $10,000 to $2,000, does that change your decision a little bit on whether you buy that car? $2,000 is a lot of money, right? So that's a large fraction of your income if you're making $30,000 a year. The larger the fraction, the more sensitive you're going to be, the more elastic your demand will be. So larger fraction, more elastic. So I gave you kind of 2 examples. For gum, gum is a small fraction. Gum is a small fraction, and therefore you have inelastic demand, or relatively inelastic demand. But a car would be a different story. A car is a large fraction of your income for most people, and therefore it's going to be relatively elastic. All right, we will call it a day there. Good job.